Now for exercise 5 of chapter 10. This is the last exercise of this chapter. Again, focused on LU decomposition and more about working with and understanding this P matrix, this permutation matrix. So now I'm writing out A equals PLU. So this is using SciPy's ordering of the permutation matrix. So instead of writing PA equals LU, I'm writing out A equals PLU. I know it's confusing because there's a bit of a discrepancy between traditional math and what SciPy is outputting, but that's the way that SciPy works. So um, anyway, we can rewrite or we can express A transpose A as U transpose L transpose LU. So there's a couple of steps that I'm omitting in here, which would be to say that A transpose A equals LU, that quantity transpose, times LU. And then I'm applying the live evil rule to express the transpose operation and then swap the order of these two. Okay, but what you notice is that I have dropped the permutation matrices. So I say that even though A equals PLU, A transpose A can be expressed without the P's. So we're just completely ignoring this permutation matrix. And why is that possible? Now, this is not a coding question. This is not a question that you solve in Python. It's a question that you solve in your brain. You have to think about it. So answer that question and then confirm it empirically in Python using random matrices and show that even when P is not the identity matrix, you still do not need P to reconstruct this expression, this equality here. Okay, so before I switch to Python, I will actually just explain why this is the case. And if you need some time to think about it, feel free to pause the video. So the reason is that when you include P in this matrix, so you have PLU, that quantity transpose, times PLU, when you apply the transpose operation to these three matrices, then on the inside, so in between L transpose and L, here you're going to get P transpose P. Now, P is an orthogonal matrix, and so P transpose times P is the identity matrix. And that means that even if you express P here as P transpose using the normal mathematics notation, then you're still going to get P times P transpose, which again is the identity matrix. So no matter what, whether you need permutations or not, this matrix P is always going to cancel itself because you're going to have either P transpose P or P times P transpose, and then that's going to be the identity matrix right in the middle. All right, I hope that makes sense. Now I will switch to Python, and I'll just show you the implementation of this expression. So here I have a random matrix 4x4. Here I take its LU decomposition. Here I'm computing U transpose times L transpose times L times U. Notice no permutation matrices in here at all. And here is A transpose times A, and here I subtract them. So if we don't need the permutation matrix, then we should find that these two, the difference between these two matrices is 0. And that's indeed what we do find over and over and over again. And here I'm rounding to 10 numbers after the decimal point, just so we don't have to look at these tiny rounding errors all the time. Now, if you would like, you can actually include the P matrix. Maybe I'll do that anyway. So let's see, times P transpose, and then, times L times U. Okay, and then we still, because this is the identity matrix, it doesn't matter if you have this in there or not.